Welcome everyone to our online NPTEL course Environmental Chemistry and Microbiology. This course will be taught by Professor Sudha Goel and myself Professor Anjali Pal. We are both from Civil Engineering Department, IIT Kharagpur. We have divided this course into two parts. The first part is environmental chemistry, which will be covered by me, and the second part is environmental microbiology, that will be taught by Professor Sudha Goel. In the lecture number 7, that is under module 2, I will explain some aspects of chemical equilibrium. I have already told about chemical equilibrium and how to set up the expressions for chemical equilibrium. Now, in this lecture I will tell about the La-Shuttler principle, which is very important in chemical equilibrium concept, and I will also tell you that how we can drive a chemical reaction towards the forward reaction or backward reaction. That means, how we can shift the chemical equilibrium. It is a fact that many reactions they do not go to completion, but they proceed to a certain extent and then they apparently stop. Then we say that the chemical equilibrium is reached. For example, hydrogen gas reacts with iodine in vapor form to form the hydroiodic acid. The reaction is shown here, hydrogen and iodine, it is in vapor form, they produce the HI, hydroiodic acid. This is also gas. So, all are in gas phase. So, this is actually, you have seen that here it is the sign where we tell that it is in equilibrium. Actually, this equation, this reaction reaches to equilibrium after some time. It depends on the temperature and the presence of catalyst, presence or absence of catalyst, but finally it gives some composition where all three will be there, hydroiodic acid, iodine and hydrogen, all three will be there, and what is the composition, that depends on the condition. Now, at that point when the equilibrium is reached, then we can tell that the forward reaction and the backward reaction they are the same. That means, the rate of forward reaction and rate of backward reaction is the same, and then we can tell that no more reaction goes on. Actually, reaction is going on, but the amount that is produced, the HI that is produced from hydrogen and iodine, same amount of HI will be decomposed to form the reactant. That means, it is the equilibrium state. The same we can explain here for the next reaction, that is iron when reacts with steam, then it will produce the hydrogen gas and the iron oxide Fe3O4. This is the equilibrium reaction. Okay. This reaction is reversible reaction, and here we think that it has gone to equilibrium stage. Now, some reactions we need to complete to 100% reaction, to make it 100% conversion. Then how it will go like that? It may go, some reactions are complete, that we all know, that we need also some reactions to be complete for analytical purpose or some other purpose. Then how to, the main question is how we can do that and under what conditions it happens. Here some examples are given. A reaction often appears to go to completion instead of going to a state of equilibrium. How it can be made? This is the question. Okay. For example, barium chloride with sulfuric acid, if it reacts, then barium sulphate is produced. This sign is the sign of precipitate. Okay. That means, in this reaction, barium chloride when reacts with sulfuric acid, it gives barium sulphate which is precipitated. and also it produces HCl. Now, when some product is going out of the phase, then the reaction goes towards the forward reaction. Why? Because you know the equilibrium expression. Equilibrium expression we have seen the reactant concentrations and the product concentrations, how it is written. So, when the product is removed, then more and more reaction will go on to produce more product. Okay. That is why the reaction goes towards the forward direction, and this type of reaction we use for sulphate determination. You know that for any analytical method of determining or quantifying something, you know that especially in quantifying something, the reaction should be complete. Otherwise, if it is not complete, then our analytical method will be wrong. So, this method is used for sulphate determination, and this reaction should be complete when we use it for sulphate determination. Now, in this reaction, in the next reaction, what you see that this is the actually laboratory method of HCl preparation. What we do in this method, we take sodium chloride, solid sodium chloride, and then we drop H2SO4, concentrate H2SO4 onto it. Then we see that HCl gas is produced, which is taken out, that means it goes away as a gas from the reaction mixture, and then more and more reaction goes towards the forward reaction. It is the same thing, actually in this case it is precipitate. So, it is going out of the phase, and here it is gas. So, it is going out of the phase, and basically the principle is same. When some product goes out of the phase, then more and more products are produced from the reaction, that means ultimately it goes to 100% conversion. Now, one interesting example is shown here, calcium carbonate. You know that when calcium carbonate is heated at a high temperature, then it forms calcium oxide and carbon dioxide. But if you take calcium carbonate in a closed vessel and heat it at high temperature, then what will happen? And when you take calcium carbonate and you heat at same temperature, but under the current of air, then what will happen? This is the question actually. When you heat the calcium carbonate taken in a closed vessel, then you will see that equilibrium is reached, and some calcium carbonate will still remain in the vessel at the bottom of the vessel, and some calcium carbonate is produced, calcium oxide is produced, and some carbon dioxide is produced, all remain together in the closed vessel. But when you heat calcium carbonate in a current of air, that means in an open vessel at the same temperature, then this carbon dioxide is a gas. So, it will go out. So, then what will happen? More and more calcium carbonate will be converted to calcium oxide and carbon dioxide. So, you see that calcium carbonate will be more amount of calcium carbonate will be converted to calcium oxide and carbon dioxide, and if you give sufficient time, then you will only you will be left with calcium oxide and carbon dioxide will go out. So, no more calcium carbonate will be there. That means, in one case in closed vessel when you heating, although you are giving the same temperature, when you are heating in a closed vessel, then you are reaching the equilibrium, and when you are heating in a current of air, that means in an open vessel, then you are going towards the completion. So, this is the case. Two different behavior means two different things we are getting when we apply different conditions. Now, what is La-Chatelier principle? This is very important in chemical equilibrium. What it is saying? What is La-Chatelier principle? It is said that if one of the conditions of a system in equilibrium be altered. So, first you have to think that we have some equilibrium state, some reaction is in equilibrium. First equilibrium state is to be attained. Okay. When something is in equilibrium, then if we disturb the system, either by raising the temperature or by raising the pressure or by introducing something. So, when we disturb the system in equilibrium, then what will happen? This is the Le-Chatelier principle. What will happen? When we disturb it, then it will adjust itself in such a direction as partially to neutralize the change of the condition. The system will act in such a way that the disturbance will be nullified. You are producing some disturbance on a system which is in equilibrium. So, what it will do? It will try to nullify the disturbance. It is shown in a very simple way, in a very nice way by using this example. This is nothing but the ammonia production by Haber's process. Okay. In that method, what we do? We take nitrogen and hydrogen, then we give pressure at high pressure, that is 200 atmosphere pressure, and we use the temperature 550 degree centigrade, then ammonia is produced and it is an exothermic reaction. So, some heat is generated. Okay. So, this is the process developed by Haber Haber-Bosch process actually, where the ammonia production he obtained from the nitrogen and hydrogen. This is also one type of nitrogen fixation, but nitrogen fixation I will discuss later in my other lectures. But here just remember that here pressure is to be given, and high pressure 200 atmosphere pressure, and also temperature 550 degree centigrade in presence of some catalyst also. This is finely divided iron as the catalyst. So, it is in equilibrium, you can see the sign. So, it is in equilibrium. Now, what will happen if, what will be the effect of temperature, what will be the effect of pressure, that we have to explain. Okay. Say for example, we increase the temperature. If the temperature is increased, okay, then what will happen? So, what according to Le-Chatelier principle, if we disturb the condition, then it will try to nullify that disturbance. That means, if we increase the temperature, it will act in such a way that temperature is decreased. How it will be done? Because it is an exothermic process. So, it will go in the reverse direction. Okay. So, it will go to the reverse direction to nullify the increase of temperature. Now, if we increase the pressure, what will happen? Okay. If we look into the number of moles, we know that number of, and at a constant volume, we know that number of moles, it is related to pressure. Okay. That pressure. So, you can see that in this side there are 2 moles and in this side there are 4 moles. Okay. So, if we increase the pressure, then what will happen? It will try to go in that direction where the number of moles is reduced. That means, when the number of moles is more, then the pressure is also higher. Okay. So, it will act in such a direction that number of moles is reduced, that means, it will go towards the forward direction. So, effect of temperature and effect of pressure we have explained. Now, considering this reaction which is also in equilibrium, say for example, NaCl and H2SO4 is producing NaHSO4 plus HCl, it is in closed vessel, say for example, that is why it is in equilibrium. Then effect of altering concentration on equilibrium, if we put it in closed vessel, then this will be equilibrium, but if we do it in open vessel, HCl will go out. That means, altering concentration means HCl is going out. So, one product concentration is becoming less. So, it will go towards the forward direction. Now, if we add NaCl, then again it will go towards the forward direction. Okay? Because this concentration increase means it will always try to decrease this concentration, and how it will decrease? By going towards the forward direction. So, this is the effect of altering concentration on equilibrium. Now, here if you see that PCl5 is going to PCl3 and Cl2. So, effect of adding a substance to a system in equilibrium. Say for example, this is a reaction which is in equilibrium. From outside you put some amount of chlorine gas inside this vessel, then what will happen? It will try to reduce the Cl2 gas. How it will do it? By going towards the backward reaction. If you increase the PCl5 concentration, it will go towards the forward reaction to decrease it. So, effect of adding a substance to a system in equilibrium, that is involved here. Okay? Adding a substance which is involved in the chemical reaction, but from outside you can introduce some inert gas also. It will have also some type of effect, but that will again just like this one. When you introduce some gas from outside, then it will increase the pressure and it will always try to decrease the pressure, and it will act in such a way that it will go towards either forward or backward reaction to reduce the pressure. That example I have not shown here, but it can obviously we can get if we understand this thing, then we can easily tell that this will happen like this. Now, how you can shift the chemical equilibrium, and here we have to apply the Lars-Hurtler principle. Now, how you can do this? This has enormous application in environmental engineering. It should be properly understood, okay, so that we can apply it for different problem solving, for different problems to solve different problems. Okay. Now, here, so first one is the formation of insoluble substances. Okay. We have already encountered some examples. Okay. Here there are many other examples I have shown, which are practical problems actually. Okay. So, here you know brass we use to make different utensils and all. So, brass, you know what is there in the brass? We remember in this way, brass and bronze. In bronze Z is there, right. So, in bronze Z is there, so zinc is not there, copper is common. Copper is common for brass and bronze, okay. But in bronze zinc is not there, in brass zinc is there, okay. So, copper and zinc, and in the bronze copper and tin. Okay. So, here there Z is there, bronze Z is there. So, there copper and tin. Okay. In this way I remember. Okay. Now, in the copper waste or brass waste, if we consider the copper waste or brass waste, then in the wastewater there is some copper ion present, okay, or zinc ion may be present. Okay. Now, how to remove them? If you look into the removal of metals, in most cases you will see that metals are removed by producing some hydroxides, because most of the metal hydroxides are insoluble. So, in this case also we can remove copper as copper hydroxide. Copper hydroxide is insoluble. So, if we increase the pH, then copper hydroxide will be precipitated and we can remove it. This way we can treat the water which contains the copper ion. Okay. But my question is that we can use NaOH, we can use KOH, that is fine, but can we use ammonium hydroxide, because it is also, and we have already learned that ammonium hydroxide is also base. Can we use NH4OH to precipitate copper as copper hydroxide? The answer is no. Why it is no? Because ammonia at the same time is a complexing agent. Ammonia, if we use ammonium hydroxide to precipitate copper hydroxide, then this copper hydroxide will not be formed, but instead it will form the cupramine complex, copper NH3 twice whole 4 2 plus, this complex. Same way zinc also, zinc hydroxide will not be produced, but instead it will form the zinc amine complex, zinc NH3 whole 4 2 plus complex. Okay? And it is soluble, these two are soluble. So, it will not be precipitated. Okay? So, this is a very nice example. And in case of hard water, you all know that hard water contains that multivalent cations, and mostly we see that magnesium or calcium ions or iron ion is there. Okay. But if we want to remove this hardness, then what we do? We have to remove it by forming some precipitate. So, what is the precipitate that we should form? In case of this, we have seen that hydroxide we have formed. In this case, in case of hard water, we have to form either as the carbonate as precipitate or hydroxide as the precipitate. Now, here we have to see that which one is more insoluble. In case of magnesium removal, if we consider magnesium hydroxide and magnesium carbonate, then from this value, this is nothing but the solubility product. I will tell you about the solubility product in my next lecture, but this is the solubility product. If we look into the solubility product values, then we can easily tell that magnesium hydroxide is more insoluble compared to magnesium carbonate. Okay. Magnesium carbonate is to some extent soluble, but magnesium hydroxide is more insoluble. So, it is always preferred to remove magnesium as magnesium hydroxide. But reverse is true for calcium. Calcium carbonate and calcium hydroxide. If you look into the solubility product values, then you see that calcium carbonate is more insoluble compared to calcium hydroxide. Calcium hydroxide is to some extent it is soluble. So, in case of calcium removal, we have to think about calcium carbonate precipitate. In case of magnesium, we have to think about magnesium hydroxide as the precipitate for the removal of hardness. That is why you know that to remove the hardness, we use the lime soda treatment. What is lime? Lime is calcium hydroxide and soda is sodium carbonate. So, lime soda treatment means we are supplying both hydroxide as well as carbonate ion to remove the magnesium or calcium ions in the appropriate way. Okay. But when we remove this one and when we remove this one, we have to think about insoluble precipitate. Okay. So, this is the for the environmental engineers, all these problems come all the time and we have to solve it. So, if we know the equilibrium concept, then we can easily solve the problems. Now, another way to shift the equilibrium is the formation of weakly ionized compound. This is a very simple example, it is the acid base titration. We know that we take some acid, then we apply the alkali to, it is some type of neutralization reaction also we can tell, and then the formation of water is there and then salt. Now, this water is very weakly ionizing. Okay. We have seen that Kw value, the equilibrium constant, that is 10 to the power minus 14. It is very low value. It is very weakly ionizing. Although it ionizes, we know, but it is very weakly ionizing. So, once the weakly ionizing compound is produced, then the reaction goes towards the forward direction, because to go to the opposite reaction, this reaction to take place, the water has to be strongly ionized. Okay. Okay, but it is not like that. That is why it goes. And for the titration, we always know that E should be complete. Otherwise, the titration we cannot use for determining something. Okay. And there is another example. Say for example, if you take ferric hydroxide, it is very insoluble substance, or aluminum hydroxide, these both are very insoluble substance. If we add H plus, that means say for example HCl there, it will solubilize. Why it will be solubilized? Because with the reaction of acid, it forms the soluble ions, and when the soluble ions are formed, that means it will go towards the forward direction. Another example with the Gelder's method of ammonia determination, means ammonia nitrogen determination. We know that ammonia nitrogen means the nitrogen present in ammonia or ammonium ion. So, in that case we make it alkaline and then we steam distill it. Then when we make it alkaline, then the ammonium ion is 100% goes to ammonia, and ammonia is highly volatile, and it will remove with the steam, and then it will be collected and then it will be titrated. So, here also it is same thing, the same principle is applied. Now, there are some formation of complex ions. So, for example, silver chloride, when we treat it with ammonia, it forms the silver amine complex, or copper hydroxide, when we put it with ammonia, it forms the copper or zinc amine complex. So, it is also by forming the complex ion which is soluble, we can make the reaction complete, we can drive the reaction towards the forward direction. Now, the cyanide, in case of cyanide, some complex formation, say for example, FeCN6 4 minus, that is ferrocyanide. When we do this, then this reaction will also go towards the forward direction, and by this way we can remove the cyanide. We can remove the cyanide containing wastewater, we can treat, and we can remove the cyanide through formation of Prussian blue, that is a complex which is precipitated. When we put this underline, then we know it is a solid substance and it is precipitated. Now, another way is that formation of gaseous product. Say for example, this is also a solid, it is reacting with the H plus to form the H2S gas, which is out of the equilibrium, then the reaction goes towards the forward direction. This is, you see that copper sulphate and mercury sulphide, this reaction does not occur. Why? Because it is so much insoluble that even small amount of H2S is also, almost no H2S is generated to drive the reaction towards the forward direction. Now, another example is that industrial wastewater treatment, cyanide, you know that this is an example of formation of gaseous product. When cyanide is reacting with the H2SO4, then HCN gas is produced, which is volatile, which goes out to drive the reaction towards the forward direction. Another process is that oxidation and reduction. You know that cyanide, it is another process of removing cyanide. Cyanide when reacts with a very strong oxidizing agent chlorine, then it produces the nitrogen gas and carbon dioxide gas, both are volatile, both goes out, and then the reaction is driven towards the forward reaction. This way we can drive the reaction towards the completion, and these are very important. Here you can see that the amphoteric hydroxide like aluminum hydroxide or iron hydroxide, which depending on pH they can form different complexes, aqua complexes or hydroxide complexes. This has been used in coagulation flocculation when we use the alum, and then these are in equilibrium, and depending on pH they are present in different concentrations. This is also applicable for the for removing the turbidity. Okay. So, this is also example of chemical equilibrium. Now, the references are the same, this is the Piquedat and Sauer-McCarty, that you can read to understand these more clearly, and also other textbooks also you can use to understand this. Thank you very much.